Good morning, everybody, and welcome to the seminar for the Department of Computer Science at Johns Hopkins University. I'm delighted to introduce my colleague, Jeremias Sulam, who's our speaker today. Jeremias did his bachelor in biomedical engineering at the National University of Entre Rios in Argentina, which literally means the university between rivers. And then he did his PhD in computer science at the Technion, where he worked with Miki Elad. He really did a fantastic PhD thesis at the intersection of signal and image processing and machine learning, where he developed models for understanding the properties of new representations for data that are related to sparsity and convolutional neural networks. He joined Johns Hopkins University in the Department of Biomedical Engineering, where he's now an assistant professor. And he's been working on many topics in machine learning, from continuing his work in sparsity to new projects in the area of robustness for deep networks, as well as applications in digital pathology. We are very delighted to have you, Jeremias, and welcome.
Thank you, Rene. Thank you so much. And it's really a pleasure to come and give a talk at the computer science department here at Hopkins. The computer science department has always been very close to Clark Hall. Ironically, now we are all talking from far away, but that's a different matter. So today, my talk is going to be centered around sparse representations, and sparsity is one form of simplicity and parsimony. And so one should ponder as to the need for these sort of simple representations of natural phenomena. And the reasons are, I would argue, profound and long studied. This is a quote by Wrench and Jeffries almost 100 years ago, who were studying basically the success of simple hypotheses in advancing science in the context of epistemology. And basically they wrote that, if you have a simple law that explains your phenomena reasonably well, you are to prefer that simple law to a more complex one that fits your observations just slightly better. And we're going to see this recurring pattern throughout the talk today. By the way, as an anecdote, Dorothy Wrench, who you see here on the left and who did most of her work at Cambridge, actually was born in the city of Rosario in Argentina, the same city where Lionel Messi is from, for those of you who are into soccer. And by the way, I should also stress, feel free to interrupt me or else type a question in the chat, and hopefully Rene will let me know. So what is this, this concept of parsimonious representations in the context of signal and image processing? Well, it's simply the observation that natural signals can oftentimes be sparsely represented. And by that, I mean that, say I take this picture, and I could have taken the entire picture, but let's say that for simplicity, I'm just looking at a little patch from this image, and I can vectorize it. I can express this patch as a linear combination of only a few columns from these redundant matrix that we call a dictionary, and we call these columns atoms. So these are basically these constituent elements that make up my real world data. And as I stressed, I can represent this sparsely, which means with only a few non-zero coefficients, as you see here on the right. Now, this very sort of simple and by now natural observation has had impact in a lot of different fields. It was perhaps made more explicit for the first time in the context of harmonic analysis with a lot of work on wavelets by Stefan Malat and Ingrid Vichy and others. Was also then taken to the realm of compressed sensing that was kickstarted, as you may all know, by Emmanuel Candes and David Donohoe 16 years ago. But it has also been an extremely important phenomenon to exploit in the field of computer vision. And indeed, if one has simple representations for data, then many inverse problems become a lot more tractable. And so there's really a plethora of applications in computer vision that have to do with reconstruction, with estimation, that have benefited from this model. Also, in the context of statistical learning, and now going back to this notion of simple hypotheses to explain different phenomenon, this was very much leveraged by groups in Stanford in the beginning, to some extent independently, actually, from the work by Candace and Donahoe, who were also at Stanford, often sitting in the same hall, but working mostly independently. And then this work was continued by Wainwright and Peter Bickel and others. And more recently, there have been very interesting connections between sparse representations and different forms of sparsity, and those representations that are computed by deep learning models. Notable works include those by Joan Bruna and among other authors. Now, today's talk is going to be about two aspects of sparse representations. One is going to be concerned about unsupervised learning, and it's going to be centered in this work on recovery and generalization in overrealized dictionaries. This is joint work with Chong and Siwi. We started talking about these ideas when they were both here a year ago for the Mainz Symposium, actually. So Mainz has some credit for this. And the second part is going to be on a supervised setting and in the context of robust learning. And this is going to be work with my PhD student Ramchandran Muthukumar, as well as Raman Arora from the computer science department. Okay, so let's dive into the first setting. So let's set the notation straight. We are going to have a ground truth model, a dictionary. It's going to have P0 columns in D dimensions, and P0 is going to be greater than D, right? So we're going to be in this redundant setting. Now, our data is going to be sampled from a distribution as follows. I'm going to have representations gamma in P0, in R to P0. And I'm going to just draw k-sparse gammas, and I'm going to draw their non-zeros normal. I don't really need these distributions to be Gaussian. It suffices that they're zero, mean, and unit variance. But for the sake of simplicity, let's assume that they're normal. And once I have these k-sparse vectors, my data is constructed as d times gamma. And I have n such examples. Okay, so the first question that one should ask is, okay, if I give you this dictionary, how can you find this representation gamma for me? And obviously, because the dictionary is redundant, if I were to write this optimization problem just with this L2 term, this would be an ill-post problem, right? I have an infinite number of representations gamma that can explain my measurements because I have more unknowns and equations. And so I need some extra regularization. That comment goes precisely for carry. And this regularization can come in different ways. I could say that, let's say that I know that these representations were k-sparse, and so I'm going to use, let's say, an indicator function that only allows for these vectors gamma to be sparse, in which case I basically have a constraint optimization problem. Or you can relax these L0 pseudo norm to the closest convex, to the closest norm, which is L1, and then you would have a lasso type problem. And there have been many, many results that analyze, when the solution to this problem actually coincides with your original gamma, with your original sparse representation. Okay, but what if you do not know D? What if you need to find your dictionary from the data? So the first thing you need to do is formalize some sort of a loss that you want to minimize, something that measures how good your dictionary is to sparsify your data. And basically, most works use this expression, and I'm just setting these laws to be how well my dictionary minimizes the cost that I showed before. Now that I have this, all I have to do during training is, let's say that I follow an empirical risk minimization approach. And what I'm going to do is minimize these laws over these n samples that I got over dictionaries in my function class, which let's say are matrices, right, with D rows and P0 columns. And let's say that also they have unit norm, simply because this is invariant to multiplications. Now, obviously, I minimize this empirical risk, but the true objective here is to minimize this loss in expectation over all the samples from this distribution of sparse vectors. Okay, so how do you solve this problem in practice, right? The problem that is written here. Well, there's been quite a bit of work studying this problem, but basically all of the different approaches do the following. You initialize some dictionary in your space of dictionaries that you're looking for. So let's say you pick a random matrix, which is D by P0. And then you update this dictionary with different dictionary learning algorithms. And you can use the KSVD, online dictionary learning, and many, many, many other dictionaries that have been proposed in the last 15 years or so. And then you pray a little bit and you hope that this worked, because the truth is that this is a very difficult problem. It's a non-convex problem. And it's still not fully understood in the more general setting when the minimizer of this problem will actually, for example, give you a global minimum of the problem that you're after. Now, for the most part, however, all these algorithms, KSVD and online dictionary learning, actually work remarkably well in practice. Okay, so on this problem of dictionary learning, there are basically two main questions that one can ask. The first one is that of model recovery. So remember, our data is sampled with some ground truth dictionary D0, right? And in the end, after this learning process, I obtain a dictionary D hat. And I want to know how far or how good is D hat compared to D0? How close did I get? And so the first thing you need to do is formalize a distance measure. So something that tells you how off you are. And a very common way to do this is to, let's say, use this distance, the Frobenius norm. And here P is essentially a matrix that permutes columns from D hat and possibly the sign as well. So basically you're asking, for all my columns in D0. Yes?
Sorry for the interruption, but could you go back to the previous slide?
Yeah.
So I understand that this formulation is very natural because the way we usually do dictionary learning is exactly in this way. Mm-hmm. But when thinking about it purely from a machine learning perspective, particularly from the perspective of having a generative model, mm-hmm. One could think backwards, namely I first sample gamma, mm-hmm. I multiply by the dictionary, and that gives me the x. Mm-hmm. And therefore, the question might be in that case whether I just consider the squared loss as my main loss, and then the expected loss is the expectation with respect to gamma, as opposed with respect to x. In various ways, kind of gamma becomes sort of the input and x becomes the output.
Sure.
So yeah. The question is, are there any differences in between the two possible formulations, or are they identical? The primary difference being that you need to take the infimum over gamma here first, as opposed to an expectation over gamma.
Right.
And what are the advantages of choosing one versus the other if they are different?
So no, there are no differences. So here is totally, so here I wrote, the expectation over x just for simplicity, but x is totally determined by d and gamma, right? So what I actually sample is gamma. So your intuition is correct. The expectation is over d and gamma, and those deterministically determine x once I have those.
Oh, but then you've written there expectation over x of fx of d, and fx of d has an infimum over gamma.
Yes. Correct. You're right. The notation is not fully precise.
Okay. So then what is it that you're doing then?
So what I could write is the expectation over d and gamma.
Expectation over d.
Sorry,
and
over gamma. Over the expectation over gamma.
Okay, expectation over gamma and including the G of gamma or not including it?
What I could do is in this loss here, instead of writing here X, I could write D naught gamma, right? D naught gamma naught. And then X here is basically an auxiliary variable. I could take X out of all this and I write everything in terms of gamma.
Great.
Great. Okay. So basically this is, now I'm in the game of measuring how far my estimate is from the ground truth dictionary, and I do this in this way. And again, there have been a number of works trying to analyze this problem. And as I said before, this problem is hard to analyze. Some works try to, for example, study when different algorithms that are already very successful actually work. Like results that study under what conditions the dictionary found by KSBD recovers the correct dictionary. Or others propose new algorithms altogether and study, and some of these algorithms come with different convergence guarantees, for the most part, without being, practical algorithms. And in any case, all of these rely, they're local convergence results. So because it's non-convex, typically you need some sort of close enough initialization in order to claim anything. And all of these results, of course, they assume that you're searching over the same hypothesis space as your ground truth dictionary, right? Now, a different question is that of generalization. So if I am totally oblivious to my, to the fact that there is a ground truth dictionary D0, let's say that I put that aside. What I really care here is that my empirical risk, which is RS, is actually not too far from the expected risk over the population. And again, there are some results. Perhaps this is the one that is the most comprehensive and perhaps complete answer to this question, work by Grimoire and his student. And basically, these results says it's a uniform bound over all possible dictionaries with P columns. And this bound guarantees that the empirical risk and the expected risk are going to be bounded by something that scales as D times P. So I remind you, these are dimensions, P is the number of columns. So this is basically the degrees of freedom of the problem, times log n over n, square root. And this is a high probability result. And of course, this result depends obviously on, for example, the regularizers that you use. It depends also on the distribution of your data. But by and large, a very wide variety of regularizers and data distributions are included by this result. And all of these share this dp log n over n driving term. Now, why do I care about generalization? Well, because if all I'm doing is minimizing my training error, my empirical risk, I can then bound how far my expected loss is going to be by this generalization gap. And the nice thing about this result is that it tells you what we need to do in order to drive the generalization gap to 0 so that my training error approximates the expected risk. Okay.
What was D and P again? Little d and little p?
Yes, D is a dimension of your data. So D is the number of rows that you have in your matrix D. And P is the number of columns, is the number of atoms.
And there is no role of the sparsity level on the bound?
Yes. And those are different constants that appear in the bound that I've excluded. Okay. By the way, the reason I excluded them is because you can write this as a function of k, but you can also write it as a function of, let's say, lambda, the regularizer penalty. And so this result can be instantiated in a number of different ways. Okay, so the question that Tsiwi and Chong and I sort of started to entertain was, all of these algorithms, and there have been many works about all this, The first thing you do is say, well, if I know that there's a dictionary D0, then I immediately search for dictionaries in the class of matrices with P0 columns. And the question is, why do we do that? Why not maybe relaxing the space, enlarging the space of dictionaries that we search over? So what we are saying is, why don't we perhaps search over realized models? And so this might be a little bit counterintuitive. So let me give you a motivating experiment. So here I constructed a ground truth dictionary, the knot, with 70 columns, okay? And I drew some training data from it, and I trained a dictionary. And the dictionary that I trained also has 70 columns. And then I compute my training error and my test error. And I get these 2 points, and whatever, this is good enough. I get some reasonable risk. Now, what I'm going to do now is I'm going to start increasing the number of columns in the dictionary that I'm optimizing over, okay? And as I do that, you see that very quickly, obviously, I totally fit the training data. Why? Because I just have way more parameters in my model, I can fit more data. Now, interestingly though, when you measure the test error actually decreases a bit for some interval, for some range of these extra columns until it starts to diverge. So until you essentially overfit. So we were a bit surprised by this, and so we were wondering if this reduction in risk had anything to do with actually recovering the model better. And so if you want to answer that question, then the first thing you need to do is generalize this notion of distances, right? Now we need a notion of distance between matrices of different sizes.
Jeremias?
Yes.
Can you clarify what precisely were you surprised by?
Yes. So you have a generated, so if I didn't know anything about the data that you're receiving, then I wouldn't be surprised. But the fact that the data that I have comes from a model with just P0 columns, I would be concerned that if I train with more columns, maybe what I recover is, some combination of those that is not going to generalize well.
Maybe, but if you get too few, then you're missing signals. So I'd rather have a few extra.
Sure, right. So if there is too few, there's no doubt about it. I'm going to be pretty bad for sure. Right. So the reason for being surprised is precisely that. Though in this case, we know we have an oracle that tells you what the complexity of your data is, and it is surprising that if you go beyond that, you still actually manage to improve the generalization.
Okay.
In any case, I would argue with Joel that, okay, you're looking at risk. So, maybe it's not as surprising. What perhaps is slightly more surprising is that reduction in risk actually comes from a reduction in the recovery error. So what I'm plotting here is this distance measure that I have here. And this is nothing else than an extension of the distance metric that I showed you before. So all I do here is my ground truth dictionary has P0 columns. And so what I'm going to do is for each of these P0 columns in my ground truth dictionary, I'm going to search its closest neighbor and then multiply it by either 1 or -1 in order to accommodate the sign flip. And that's it. And this is going to be my distance metric. And of course, this boils down to the previous distance if you happen to have the same size. So if you plot this, you see that actually the recovery error decreases, which means that this reduction in risk really comes because you, in this extra number of atoms that you're searching over, you actually are finding a subset P0 that are closer to your original P0 atoms. So this is one part of the puzzle. The second part of the puzzle is what happens when you change the number, when you vary the number of training data that you have, because all these results hold for some given n number of sample points. So as you increase the number of training points, what you see is that actually both of them improve. So as you train with more data, you can reduce not only the risk, but also the recovery error. And again, the surprising thing is that you can increase recovery by looking over dictionaries that are over-realized, that are larger than your grand truth model. Now, let me stress again, Jovo, that we were not just the only ones saying that this was surprising. So I think that the very first manifestation of this was by Dasgupta and Sulam, who sort of found something similar in k-means. As you may well know, k-means is a close cousin of dictionary learning. And they found that if you want to recover the clusters with k-means, you can actually do better if instead of searching over k-means, you search over slightly larger set of means. Only this year, and actually work that began last year, students of Ristesky and David Sontag also showed basically what I'm showing you right now, although they showed it essentially just in an empirical study and for slightly different models. But basically they were coming out and saying, hey, everybody, this is surprising. You can actually improve recovery empirically if you increase the class of, if you increase your search space to include models that are larger than your Oracle one. So as you can imagine, we were very much inspired by this work of Sontag. Yes?
Two quick questions.
Yeah.
The first one, why is this an adequate metric for comparing the true dictionaries?
Mm-hmm.
In particular, the dictionary columns are permutational invariant, so one should be doing some sort of joint matching of multiple columns. Otherwise, many columns could be assigned to the same or something like that, no?
Yes. So two answers for that. The first one is, look at the permutations actually taking into account here, right? So for a fixed I minimize over J, right? So I am doing this matching process. Yeah. And it is true that different J's could be assigned to the same I, but this is a good metric because this is going to be 0 only if each atom in my Oracle dictionary has a neighbor.
Okay. It's because it's yeah, obviously because it's overparameterized.
Yeah.
And my next simple question is, in the plots, where is P0 exactly again?
Great. P0 is on the left. So I'm starting from 70 because my ground truth had 70. So all of 15 years of research in dictionary learning would have given you these 2 points here. All we are doing is saying, hey, maybe it's worthwhile actually looking over larger dictionaries in the hope that you will improve your recovery of your ground truth dictionary, which has 70 columns. Okay, so basically the main result that we have to sort of characterize this phenomenon comes from basically tying these two somewhat disjoint views on dictionary learning of recovery guarantees and generalization bounds. And so this is going to be slightly more technical, but bear with me. And so here, F I had denoted before as the cost, right? I'm going to make this more precise. I'm going to take my cost F to be this L2 difference, my reconstruction error, with vectors that have a cardinality of S. So with L0 constrained vectors. And mu is, of course, as you would expect, the mutual coherence of the dictionary, which measures how correlated the columns on the dictionary are. So what we can show is the following. Turns out that if you have a generating dictionary D0 with P0 columns, and you give me n training samples with a sparsity of K, then for any dictionary D with P columns, P is independent of P0. For any P, I can bound the recovery error, which is this distance that I showed you before, by basically my training error, my empirical risk, which I can compute on my training samples, plus my generalization gap. And another term that I will get to in a minute. But why does this make sense? Because this basically describes the phenomenon that we were seeing before, namely, I want to decrease my recovery error. Okay, I can do that. How? By increasing the number of columns that I have. Why? Because if I increase my model size, I'm going to be able to decrease my training error. Now, what I need to do at the same time is increase my number of samples so as to compensate for the increased complexity of my model. Now, the little detail here is that this training error is measured over samples that have a sparsity of 1, right? So if my samples are generated with sparsity of k, I'm measuring my training error for this bound just with samples that have a cardinality of 1. If k is equal to 1, then this is tight and this is fine. But in general, if k is greater than 1, then we have an extra term that essentially compensates a bit for that slack. And this term here is going to be positive, so this is going to give you a tighter bound to your recovery error under some regular conditions if k is small enough. So by and large, what this result says is this phenomenon that you can decrease the recovery error can be explained by looking at generalization bounds, because I can decrease my training error by increasing the model size, as long as I increase my number of samples accordingly to compensate for the generalization gap.
Jeremias,
Yeah.
could you go a little bit more into the zeta k times k minus 1 term?
Yes, sure. So as I said before, this term comes into play because you see, if my data was generated, say, with 2 non-zeros, okay, and I'm sparse coding it with only 1, if you will, obviously I'm never going to achieve 0 training error, even if I had my ground truth dictionary, right?
Right.
Okay, so this is what this zeta k is accommodating for. This is saying, well, this excess risk that you will have can still be upper bounded by zeta k. And zeta k is this expression that you see here. Now, in order not to make this trivial, then you can take the max of 0 and this expression. This expression depends obviously on k, depends on the mutual coherence of your dictionary, and on another constant that has to do with the cross correlation between your estimate and your ground truth dictionary.
So as sorry, just last point. So as k increases, the recovery error goes down. Okay, yeah, that makes sense, right? Okay.
Yep.
Okay.
Excellent.
So I expected, the generalization gap increases with P, and therefore it will increase with the amount of overparameterization.
Yep.
So I expected the middle term would compensate. Well, it's negative, so the middle term would increase by increasing the overparameterization, but it only seems to depend, at least evidently, on k, but not on p minus p0.
Correct. Correct.
And so how do I know that by overparameterizing I am improving? Okay.
So you know, simply because by overparameterizing, regardless of what your data is, right? By overparameterizing, you can reduce your training error.
Mm-hmm.
Right? Great. That's it. What is also, so you're decreasing this term. Now, what is also increasing is your generalization gap, because the complexity of your model increases.
Yes.
So the controlling knob here comes to be the data. The data, the relationship between P and N is what gives you here the control.
Mm-hmm. But then I need to know that the reduction in the first term is smaller than the growth in the third, at least in some range.
Sure. So yes, so this bound, as I said before, is not tight, and so you cannot directly put here a precise. You cannot derive from this a optimal P, if that's what you're asking.
Yeah.
We cannot tell you what is the optimal P to use.
Yes. By the way, you're trying to make me a notation invariant between the S and the K and the P primes versus P's and P zeros.
So they are all actually different, so they shouldn't be invariant.
Okay, so what is the difference then between S and K?
Yes, K, I apologize, it's a bit technical. So K is a ground truth sparsity of the data that I'm seeing. This is part of the generative model. S is simply a parameter that tells me how do I want to measure my risk, which might be different than K, right? In this case, I'm measuring my risk with a cardinality of 1, even if K might be different than 1.
Well, why would I want to use a S different from K?
Because this is how we actually can bound. Otherwise, we cannot give you an upper bound for the recovery error. There are two things happening here, right? One, only things about generalization of models that you're learning and learning bounds. The other say, well, you're actually after a particular ground truth model. So how can you marry these two? And the reason that we measure this with a cardinality of 1 is technical, but is because of the proof. We would love to have a result that here has a K, but at the moment we cannot give you that. Okay, so here's the follow-up question. I hope I convinced you that you can, in this larger set of P or P prime columns, there's a subset that seems to recover your P0 better. So the question is, could you distill that larger model and recover the subset that is actually best? So to show you that you can actually do that, here is another motivating example. This is the same curve that you saw before. This is the recovery error as a function of the dictionary size. The ground truth dictionary always has 70 columns. Okay, so if I have 70 columns, I get this error in recovering my model. As I search over realized dictionaries, my recovery improves. This is the same that we've been seeing so far. So I'm going to take a point here where the dictionary that I trained has 100 columns. And I'm going to try to diagnose what's happening. And so I'm plotting here how far are each of these 100 atoms to the ground truth atoms. So I'm plotting their similarity. So very low means that they're very non-similar, and very high means that they are very similar. And I'm plotting this as a function of how often the atom is used in the training data. And so what you see here is that there's these two clusters of things, right? There are some atoms that are very close, as you would expect, very close to your ground truth atoms. And these are the ones that are used the most. And there's another cluster that is very dissimilar and that they are pretty much not used. Now, this is natural, but it's also really good because this quantity on the y-axis I cannot compute, but the one on the x-axis I can compute. And so I cannot say, okay, if I knew that my dictionary had 70 columns, let me just take the first 70, right? The 70 that I used the most. And then if I see how good did I do, well, the ones in red are the ones that would be the oracle ones. So the ones that, had I had the ground truth dictionary, those are the ones that you should have picked. As you see here, by picking the ones that are used the most, you don't pick the oracle ones exactly, but you get pretty close and you introduce a little bit of error. If you measure that error, you will see that actually the recovery, the error increases slightly, but not so much. It's still pretty good. And so if you do this for every dictionary size, you see that for a pretty decent range of overparameterization of the parameterized quantity, by searching over these overrealized dictionaries and then distilling the model down, even with this heuristic that I just told you, you can actually improve the recovery significantly if you compare it to what you were doing if you were just doing, let's say, traditional dictionary learning. with just 70 columns. And then this deteriorates as you search over larger dictionaries. Now, this phenomenon of being able to distill down the best P0 atoms within this larger set is something that doesn't just work in this particular example. This actually works across a wide variety of settings and parameter and model parameters. So what I'm showing you here is a recovery error. This is the minus logarithm of the recovery error of traditional dictionary learning. Okay, you're searching with dictionaries with the same number of columns as your ground truth dictionary. And what you see here on the y-axis is the redundancy of your model, and on the x-axis, the density of your representations. So these two parameters basically control all of the parameters of your model. Now, if you repeat this experiment, but now while searching over realized models and then distilling down, you basically improve always, sometimes more, sometimes less, but you always get an improvement, sometimes a very dramatic improvement over what you can do with just traditional dictionary learning. These are numbers for the recovery error, and then naturally the risk improves accordingly as well. And this is something that holds no matter what, basically. You can use different learning algorithms, you can use methods that are batch learning algorithms like the KSVD, or you can use stochastic optimization methods like online dictionary learning, or you can use L1 regularization, or you can use L0 regularization. And these results of improving by searching over realized models is consistent across all those cases. And it is also robust to contaminations of noise, which I totally excluded here, but I'm not going to delve into those results. This heuristic that I was describing of how to distill your model down is actually not so much of a heuristic. So we have some guarantees for this. And what we can prove is that if the estimate that you receive that has P prime columns, which has, I remind you, P prime is larger than P0. If within this larger set, you have some M columns that are epsilon close to the ground truth atoms, and another set that is epsilon away, which is basically the setting that you see depicted here. So the black are the ground truth atoms. What I'm saying is, what seems to happen from the results that we've seen is that there is a subset of them, the ones in green, that are close to the original ones, epsilon close. And there is another set that is pretty far away, as you see here in red. So under this setting, for some value of epsilon and for some k, doing this distillation procedure that I just described actually recovers precisely the ground truth, the oracle choices of those subsets, the ones that actually are the closest. So this is why this distillation procedure actually works.
I had a question.
Yes,
just to make sure, atoms are the same as columns. So when you say atoms, it's another, like, I guess, word for columns.
Correct. Atoms are the columns of your dictionary D, which is also the matrix. Yes.
Okay, thank you.
You're welcome. Okay, so with this, I want to do a very quick summary and move on. And basically, what I showed you is how to tie this question of recovery with tools from learning bounds. And also an important thing to mention here is that we don't fully understand the phenomenon here, and the phenomenon has to do with really the optimization landscape of the problem that we are solving. And we don't really know why this is the case. We have some hints. So, for example, if I were to plot the minimal number of times an atom is used as I increase the number of columns in my dictionary, it turns out there's actually a pretty sharp phase transition. So my ground truth dictionary has 70 columns, as always. As I train with larger and larger and larger models, at some point, the moment I go beyond the ground truth size, this clustering phenomenon that I described appears. And so there are some atoms that are pretty much not used at all. So more work is basically needed to understand fully what is happening from an optimization point of view.
Jeremias, when you say that there's minimum atoms used, this is only at the convergence, so at the with the learn dictionary at the end, or is this during learning?
No. This is at convergence. At convergence.
Do you track how often the two clusters are being used during learning itself?
No. No, we haven't done this. Yeah, are there more questions?
So, do you think this is affected by the choice of the optimization algorithm, or is this all learners of a specific, say, ERM would exhibit this property?
Right. No, because of what I mentioned before. So this phenomenon is consistent across different learning algorithms. So there's something, I think, more fundamental happening here. And to be honest, also evidence for these being way more general than just the learning algorithm is that this has also, as I showed you before, this was also reported in some graphical models in k-means. So it seems to be something pretty fundamental about latent variable models in general. Okay, so in the time that I have left, what I'm going to very briefly tell you about is some work on a supervised setting. By the way, excuse me, Rene, how much time do I have?
About 12 minutes.
Okay, so here we are addressing questions of robustness. And so probably you already know that adversarial examples are little perturbations to the input that can totally confuse machine learning algorithms. So in this case, I have a classifier F that correctly predicts that this picture is out of a panda. But if I perturb it a little bit with some imperceptible noise to humans, then the network automatically predicts that this is something totally different. Now, you might think that this is just a toy example, but in reality, this is a very real problem. So this is a work, for instance, by people who 3D printed a turtle that is recognized as a rifle, pretty much, by any common object detection algorithm in the wild, in the world. You can use these things to hide yourself from computer vision systems. So, Tom showed that you can print these coats that basically prevents object detection and people detection algorithms from detecting you in a crowd. So these are very important problems. And so to be a little bit more formal, here we have an input space and an output space. Now the output is, in this case, the space, the set of binary labels. And I have a hypothesis class from X to some Y prime that may or may not be the same as Y. In this case, it's the reals. And I have a bounded loss that measures how good a particular hypothesis is to predict Y from X. And I want to minimize, again, the expected risk. But I do that as an empirical risk minimization problem. So I minimize this risk over n sample points. Now, in this adversarial setting, what I want is not just to be good in minimizing my, say, classification loss, but to be robustly good. And by that I mean that my loss is going to be it doesn't just measure F to predict Y, but rather it measures how good is F when the inputs are perturbed by V, and V live in a particular bounded set. So in this case, let's say that it has a bounded L2 norm. And this is simply the empirical version of this robust risk. So the question is, what should your hypothesis class be? So obviously, you could look over linear predictors with bounded norms. And, these are, in this case, the theoretical underpinnings of this is very well understood. However, linear predictors are not typically applied to data directly because they're very, very limited. What typically happens is you have some learned representation. So you have some representation mapping from your input space to some feature space in p dimensions. And then you have a linear classifier on those representations. And then on the one hand, this is great because this enables for a much richer class of representations and of predictors. But this becomes very difficult to analyze, particularly when this mapping is data dependent and nonlinear. So what we decided to do was to sort of compromise and say, well, let me study a very particular case for this encoder, for this feature representation. And that is going to be the one that I obtain as the solution of my sparse coding problem. So again, my representation of my data is going to be given as the solution of this sparse coding problem. And so the whole hypothesis is going to be linear predictors composed with this representation. This, by the way, also makes sense, from a historical point of view. These kind of models were very heavily deployed in computer vision before the advent of deep learning, and so it's a very natural model to study. Now, lasso, because D again is redundant, this is a convex problem, but it is not strongly convex, and so we need a few assumptions to be able to say anything about this. The first assumption is, as you can imagine, that the dictionaries are RIP, which means that basically for sparse vectors that are S sparse, they behave close to an isometry. So their norm in L2 doesn't change too much. The second assumption, and this is, you might be familiar with this is very standard. The second assumption, which is a bit less standard, is that of an encoder gap. So what does this mean? This is simply saying, take your residual. This is, right, I have my X, this is my encoded vector, and then compute the residual, how good you did in encoding your data. And then compute the inner product with your matrix. Now, you can clearly see that if there is a non-zero element here, then by optimality conditions, that's going to be 1 times lambda. And so basically what this tells you is this gives you a measure of how good D sparsifies your data for some parameter choice. Now, we're going to assume that this encoder gap is positive, and this indeed holds for example, k-sparse vectors or approximate k-sparse vectors. But more importantly, it holds for real data, and you can measure it from data directly. So, for example, here I have a model that I've trained with MNIST digits, and for a given parameter lambda, if S is, let's say, below 25, then this measure of encoder gap is 0. Simply because there are, let's say, 25 entries that are non-zero. Now, if I increase S, the data is still has 25 non-zeros. And so for the other 0 elements, the optimality conditions tell me that this quantity here is going to be positive. But importantly, I have a knob here to control this. I have my choice of S, which again is not the cardinality of your data, it might be larger. And I have my regularization parameter. The larger lambda, the larger I can get this quantity to be. And this holds again for MNIST, CIFAR, this is a very natural phenomenon. This basically says you can sparsely represent natural data. Okay, so the first result I want to show you is that, there are many results that talk about how stable the representations by lasso are. But what we have here is a result that says, well, if your encoder gap is large enough, then the representations computed by lasso are stable. And the nice thing about this is that it gives you a very direct control over the parameter S. So you can increase the encoder gap by increasing S at the expense of worse constants here with the RIP. So I'm running out of time. And so what I want to show you is that you can use this notion of stability to certify the robustness of supervised models. And so the result that we have is that if you have a margin which is positive, and you have an encoder gap for that sample X. If you have this F, which is, I remind you, this supervised, this hypothesis, which takes an encoding and then applies a linear classifier on the encoder features, this predictor is not going to be altered, it's going to be unperturbed by adversarial contaminations, as long as the energy of the perturbation is no more than neither something that has to do with the encoder gap and something that has to do with the margin in feature space. And so what this basically says is that these robustness properties lost when either the contamination is big enough to corrupt your encoding, or when it's large enough to perturb your features beyond the margin. Now, obviously, the RIP is not computable, but you can have efficient. Well, you can find upper bounds for it that are computable, and this gives way to a pretty direct way of computing these bounds in practice. So what you can do, and I just want to move forward, I can come back to these if you have further questions. You can use these tools to certify accuracy. So for those of you who are aware, who are familiar with certified smoothing is a way of certifying the robustness of a predictor by composing it with a Gaussian. But importantly, what you're certifying is the robustness of G, right, which is different than F. Now, we can do something very similar in terms of certified accuracy. It's basically the same performance as that of certified smoothing. But the difference is that certified smoothing doesn't assume anything about F, and therefore it has to rely on some sampling procedure to provide these bounds, and they are actually high probability bounds, they're not deterministic. Whereas in our case, because we know a lot more about how F is composed, we know a lot about this encoder, then we can give you bounds that are deterministic and trivial to compute. So you can compute these bounds basically trivially. So this is very, very briefly, and I'm a little bit rushed, what I had to tell you, basically how one can exploit this notion of stability of learned representations together with a notion of margin in the feature space to analyze the trade-off in the setting of robustness of predictors. And that comes, the benefit of doing this is that you can end up with deterministic and very efficient robustness certificates. Obviously, for those of you who might know, these may be very closely related to multi-layer sparse models and deep networks. And one can ask, what are these more generalized notions of gaps or stability for more general representations? So thank you very much. That's everything that I had for today, and apologize if the last part was a bit rushed.
Thank you, Jeremias. I guess if the floor is open for questions, I was looking at the chat. There was one from Professor Cooper. I don't know if he's still around.
Well, I don't see the
I'm still here.
Yes. I don't fully understand the context. You must be referring to some slide.
Okay. So I know about using turtles and patches and things to confuse machine learning that sits behind cameras, for example, or other 2D sensors. Does this same spoofing technique work if my sensor captures true 3D information, such as a LiDAR?
I believe so. Basically, and the reason I say I do is because if you note, all of these adversarial attacks, real adversarial attacks in 3D, have actually been implemented by 2D things, right? So you typically print like the t-shirt, right? You print a pattern. Oh, sorry, your point is that in 3D you would not be able to be perturbed by those. Excuse me, now I understand the question better. You're correct. Now, I am not familiar if people have device attacks for 3D systems. I would expect that to be the case, but I don't know.
Thank you.
Right. The next question is from Professor Keverkidis.
So a quick question, Jeremias. Do you get at some point some degree of interpretability included in all of this? Have you gotten there to include some sense of, as you get more or less, how much sense it makes?
Yes, it's absolutely. So the broad answer is yes, but let me be more specific. Are you asking about the first part of the talk or the latter?
Yeah, the first part, not the adversarial. As you take more and more. And
I see. So we haven't thought of interpretability in that context so much, but what I can definitely tell you is I can always look back and see what are my atoms that are used the most. And okay, and that definitely tells me something, right? So if I have,
I appreciate that. My question is, I was kind of more asking, have you thought at some point, or would it come up, that by enlarging the dictionary, you get better representation, but worse understanding?
I see.
Better reconstruction, but worse understanding. That was
excellent. That's a very, very good point that actually I hadn't thought until now. But the answer is actually no, because what I was showing you before is that by searching over these overparameterized space, you can still prune back the smaller set. So you still get to recover and to interpret what those atoms are.
But you would agree with me that if the thing is overparameterized, then on your data, some of your components must be functions of other of your components that you already have. So there is this redundancy, and you can even test it or learn it or something.
Yes, I agree. If you have generative models assumptions, then it's not as bad. But yes, I agree with your comment.
Thanks.
Okay.
All right. Are there any other questions?
Yeah, I was wondering actually also about the pruning. How do you do that if you don't know the true P naught, right? So for example, Kirkland-Lewicki, Brunel, Schausen have used methods like adding an L2 norm over the dictionary in order to, kind of prune away on the go. Would that work here? Is this a way of, giving additional theoretical credence to those kind of practical techniques?
What was the first part of the question? How do I do the training?
The pruning.
Oh, the pruning. So the pruning basically just does sparse coding. What I do is I obtain a model. I want to prune it. What I do is I'm going to sparse code data, my training data, say with OMP, and I'm going to pick, if I know that I should recover 70 atoms, I'm going to pick the 70 atoms that are used most frequently and discard the rest. That's it. And what we've shown is that if you do that with OMP, then under some assumptions, then that is provably correct. You could also do it with L1 probably, but we don't have a guarantee for that.
All right. Well, if there are no further questions, let me thank Jeremias for a great presentation, and thank you everybody for attending.
Thank you so much, Renee, and everybody.
Hey, Harry.